as Samira. My roll number is 219518041. Today my subject is embedded system design. Today's topic is real-time fault detection and diagnosis system for analog and mixed signal circuits of acoustic. Introduction to fault detection. Fault detection is critical in maintaining the reliability of analog and mixed signal circuits. Acousto-optic devices are particularly sensitive and can exhibit faults that compromise performance. A real-time system is essential for timely identification and resolution of these faults. Importance of real-time systems. Real-time fault detections ensures minimum downtime in circuit performance. Quick diagnosis can prevent extensive damage and costly repairs in complex systems. Continuous monitoring allows for proactive maintenance and improved system longevity. Introduction. The electrical power system is complex network of power generation, transmission and distribution that provides electrical to end user. Recently, EPS has become more complex due to renewable generation, electric vehicles, energy storage system and smart grids. A critical challenge in operating EPS is maintaining the stability and quality of the delivered products. Power quality disturbance (PQD) caused due to various reasons including equipment malfunction, weather condition or issues in electrical lines may cause significant damage to EPS, leading to equipment failure, blackout and economical losses. Moreover, EPS damage caused due to a fault increase over time. Hence, early detection of the type and location of PQDs is important to mitigate the effects of PQDs, protect and restore the EPS and prevent cascade damages. Power quality in EPS is monitored by measuring voltage and current signals, and there are several standards and protocols to detect PQD based on the measured power quality. On the widely recognized standard for PQD is IEEE 1159 standard. This standard provides guidelines for monitoring and analyzing PQDs in EPS that covers a range of power quality issues including voltage swell, harmonics and interruptions. The IEC 61000 series is also well-known standard for managing EPS, providing guidelines on the power system design, installation and maintenance of the EPS to ensure that it meets acceptable level of power quality. Although these standards suggest reference values for various fault scenarios, it is challenging to establish protocols that cover all fault conditions due to the complexity and non-linearity of EPS. Recently, deep learning has been proposed as a potential solution to overcome the aforementioned limitations. Deep learning, a subclass of machine learning techniques, has been rapidly developed and demonstrated to be capable of analyzing both linear and non-linear systems without manual features extraction or optimization. This is because deep learning is capable of training a model from data. In the field of PQD detection is EPS. Various deep learning models including convolution neural network (KNN), recursive neural network (RNN), long short-term memory (LSTM) and autoencoder has been proposed to enable accurate fault detection via deep learning. Our previous work proposed that the deep learning model can accurately detect EPS faults. We demonstrated the feasibility of the proposed idea via a deep learning model consisting of several convolution layers, fully connected layers and synthetic data. Although this work successfully demonstrated the proof of concept of exploiting deep learning for PQD's detection, the data used for training and a deep learning model have voltage information before and after PQDs, indicating that method did not enable prompt actions for protecting the power system from PQDs. This is also why many previous works utilizing deep learning for PQDs detection could not perform real-time operation. This study proposal of real-time method for detecting PQDs is in a power system as early as possible by harnessing the data segment approach with transform-based learning models depicts a schematic of the proposed method for real-time fault detection using deep learning. The voltage and current waveform oscillate over time of the frequency of power generated in the power system. When a fault occurs on a certain line or bus, there are significant fluctuations in the signal in the power system. Segments of electrical signals are fed into the deep learning models as inputs to immediately identify the fault type and location. If there are abnormal signals in the segmented data, the deep learning models can detect fault conditions. This is the core concept of the real-time PQD detection methods, which cannot be achieved when using the entire voltage signal as the input to deep learning models. In summary, the main contribution of the present work, small segment of voltage signals used as the input of transformer-based deep learning models allowed for real-time fault detection. A transformer-based deep learning model outperformed a CN model as it utilized global content and long-range dependencies of segmented data, even though there were limited fault-related data points. The proposed method enabled accurate fault detection using data acquired under limited PMU conditions, indicating this method has the potential to be applied in the actual power system. Fault detection scheme. Fault detection scheme. The majority of data used in this study were stimulated under normal conditions. If accuracy was calculated during the entire data set, it may result in the higher accuracy value that does not reflect the real-time fault detection capability of the proposed deep learning model. To address this issue, a new evaluation method was defined to assess the real-time fault detection performance. Specifically, the accuracy and fault detection time was calculated using only 5 data points before and after fault onsets. This approach provides insight into the accuracy and set of the proposed deep learning in detecting faults in power system. Overview of analog and mixed signal circuits. Analog circuits process continuous signals, while mixed signal circuits integrate both analog and digital components. Faults can be arise from various sources, including components degradation, environmental factors, and design flaws. Understanding the unique characteristics of these circuits is crucial for effective fault detection strategies. Common faults in acousto-optic circuits. Typical faults including signal distortion, amplitude fluctuation, and phase shifts. Other issues may involve thermal dip, noise interference, and component failure. Identifying these faults early can help mitigate impacts on system performance. Methodologies for fault detection. Methodologies such as signal integrity testing and parameter monitoring are employed for fault detection. Advanced algorithm including machine learning can enhance fault identification capabilities. A combination of hardware and software solutions can optimize detection processes. Real-time monitoring tools. Modern systems utilize oscilloscope, spectrum analysis, and dedication fault detection hardware. Software platform can visualize data and provide real-time alerts to the operators. Integrations of IoT technologies can facilitate remote monitoring and diagnostics. Diagnostic system. Diagnosis involves isolation of fault and determining its root causes.
Techniques such as signature analysis and simulations-based detectors are commonly used. Analyzing historical data can improve the accuracy of fault diagnosis over time. Implementation challenges: real-time fault detections in existing cases, ensuring system reliability while maintaining accuracy can be complex in mixed signal environment. Additionally, compatibility with existing interaction will pose integrated difficulties. Cost studies and applications: various industries, including telecommunication and medical devices, benefit from these systems. Case studies illustrate the effectiveness of real-time fault detection in enhancing operational efficiencies. Lesson learned from the applications can improve future developments in fault detection technologies. Future direction and innovations. The future fault detection lies in the integration of AI and machine learning of predictive diagnosis. Continued and advanced in sensor technologies will enhance monitoring capability. Features in novel material circuit design will also lead